Hi, my name is Michael Rascher, and this is my submission for the Innovate ECE Challenge for the Bioengineering thread. Today, I will be demonstrating an sEMG detection board which amplifies and filters a muscular sEMG signal for display on an oscilloscope. In this demonstration, you can see that the signal is relatively flat when at rest, and when the muscle is flexed, a clear signal emerges. The sEMG board also works for a variety of muscles across the body. For example, on the tricep, the signature of the sEMG signal looks like this. The sEMG detection board can even capture muscle activity from the shoulder. This is an sEMG signal for the forearm. Notice that at rest, the peak-to-peak value of the signal is under 5 millivolts, while when flexed, it rises to about 30 or 40 millivolts. In purple on the oscilloscope, we are now looking at the FFT of this signal for the forearm between 0 and 500 Hertz. Notice that when flexed, all of the frequency content in this range increases.
The design of this board was accomplished with a series of analog filters and amplifiers. First, the signal gets passed through a 10 MHz low-pass filter to reject RF interference. The subsequent diode ladders provide ESD protection for the circuit from any sudden motion or muscular activity. The signal is then boosted with about 20 times gain using an instrumentation amplifier. Gain is effectively determined by the ratio of the 10 kΩ resistor to the 510 ohm resistor. A third reference electrode is included at the bottom of the schematic for common mode rejection, often known as right leg drive in the bioengineering field. The frequency content of the signal is then restricted to the anticipated range of a normal surface electromyogram, which is about 15 to 500 Hertz. A passive high pass removes frequencies below this range, while a second order active low pass removes frequencies above this range. A unity gain buffer separates these filters from interfering with one another by managing input and output impedance. Finally, a notch filter at 60 Hz prevents power line interference. Half supply is generated here for virtual ground to properly bias the op amps. For this project, the output is viewed on an oscilloscope instead of being passed into an ADC, so we can ignore the AC coupling. In Altium, each schematic corresponds to a subsection of the circuit for ease of readability, despite the flat hierarchy structure. The finished PCB layout contains bypass capacitors near op-amp ICs and a split power plane to accommodate the half supply. This is a rendering of what the finished product looks like. After ordering all of the components and the board itself, I set to work soldering it all together. Using the Hive makerspace, I honed my surface mount soldering techniques for the main reason that I was too cheap to buy the stencil for my design. My main strategy was to apply solder to one pad, place the component on the pad, melt the solder to secure one terminal in place, and then solder the other side. Tweezers and steady hands were key. Ultimately, the completed PCB looks like this, and I can confidently tell you there's no greater feeling in the world than looking at a working PCB you've assembled all by yourself.